what happens here is that in Zoom, I'm allowed to record the session, and I do record it, and I do post it on YouTube, but I post it in a private way that only people with the link can see it. So although, yeah, it is on YouTube, and I don't know what the capacity of Brightspace was, but or is, but the capacity to upload all of the videos on Blackboard were not, it wouldn't handle all of the videos. So that's why I use YouTube, but it's private. Only your classmates will and myself will ever see those videos. So don't be afraid or concerned about someone outside of this class seeing those videos, unless one of your classmates shares the link. Then of course someone would be able to see it. So don't be concerned about that, but it's recorded. I'll post the link to the video in the Brightspace content area. So when you're taking your quizzes or your exams and you're not quite sure about the answer, you might want to go back and take a quick look at that, because as I said before, these are phone a friend, use any resource that you want to, exams and quizzes. So I'm not monitoring them in any way. So use that freedom to your best advantage. But at the same time, as I illustrated before, it makes a lot of sense to double check if you're going to call somebody up and say, what's the answer to number so-and-so? It makes sense to double check, say, how did you get that? And then go through the process just to double check their math is right, that their assumptions are right, that they put the variables in the right location into the formula, if there's such a thing. But it's entirely up to you. So you can see the slides we talked about. Well, we got to talk about attendance and the project and the recording. So the recording, I think everybody should feel comfortable about that. Don't hesitate to ask a question. Specifically, if you don't understand something, I suspect that it's not your fault. It's my fault for not explaining it correctly or thoroughly. So do not ever hesitate to say, hey, Professor Bryce, I don't understand what you just said, or I don't get it, or how does that work, or it doesn't make sense to me, or whatever. Recognize that there's very likely one or more other students in the class who are so happy that you asked that question. And of course, I'm happy that you asked that question, because my job is to share what's up here with you. And if I fail to do that, then I'm not doing my job. So don't ever hesitate to say, don't be of the mindset that you don't understand what I'm saying and it's your fault. You're here because we think maybe the elders sharing some of their knowledge with the youngins will help you out in your career. I doubt very much if anyone's here in this university just for the fun of it. I think you're trying to build a foundation of assets that will look good to a potential employer or will benefit you as you run your own company. So don't hesitate to say, hey, I didn't quite understand that. Make sure to talk about it and share that thought. But if you're uncomfortable doing that, you have in the syllabus, it has my phone number, and you're welcome to text me and say, hey, I didn't quite understand this, that, or the other thing. And I'll be happy to take a few minutes out of my time to go back in and share with you. So also, we have our office hours are Mondays from 9 to 11. They're always online. And if you want to take advantage of that, I recommend that if you're doing your little baby steps towards finishing this project or attacking this project, that you come into the office hours and say, Professor Bryce, help me out. And I'll warn you, as you probably know, that as we approach the end of the semester, if you're waiting till the end to do your project and then you're waiting till the end to ask me for some help, that there are many other students like that too. So this Monday, we didn't have anybody come into the office hours. It's early in the class semester. But what's going to happen is it's going to get more and more filled and more and more filled, and you might not be able to get your question answered during the office hours because there's so many other students in there. So it makes sense to start taking advantage of that if there's any questions or lack of clarity that you have. As we go through the project, don't hesitate to send me a text message. Just because of my office hours are from 9 to 11 on Mondays, doesn't mean that, as I sit here designing houses for other people, I'm sitting here playing what I call playing video games using Revit. And so quite often I can stop for 5 minutes or 10 minutes just to help you out, and I have no problem doing that to help you out. So I'd like to convey to you that you have that opportunity in the event that you don't understand something and you want to get a clarity. It doesn't have to be during the office hours. I'm almost always available. But if I'm not available, I'm on a job site or on the phone with a client, we'll schedule something very quickly to keep you moving forward and understanding what's going on in the class and the project, which is the next thing I'd like to speak about is, does anyone have any questions or thoughts or ideas about the project?
Yes, Professor. I was trying to do a question I asked when I was looking at the one of the wall sections. I think it's wall section C, if I'm not mistaken. Um, how do you determine if it go all the way around the house or not?
That's a good
Um,
question.
yeah,
That's a very good question. Because again, I recognize you might, not you personally, but someone in the class uh, might not have any experience in looking at blueprints or blue plan. We call them blueprints. We used to use ammonia to print them, and they were blue. They're not blueprints anymore. But anyway, let me pull it up and I'll share it on the screen and we'll go through it, because if you have that question, I'm sure that other students do too. So let's take a moment on the project. I have to pull it up first, so give me a second to get to it. And then we'll take a look at wall type C, as what you were saying is the
yeah, because what I assumed is that wall type A and wall type B goes around the full house because I think that's a basement wall. But I wasn't sure about wall type C. I might be wrong about wall type A and B as well. I'm not sure.
All right. Well, it's coming up now on my other screen, and then I'll drag it over. Oh, here it is on this screen. Are you seeing the plans now on my screen? Or do I have to do something different with the display?
Yes, Professor, I'm seeing it.
Okay, so let's go. We're going to go take a look at wall type C just to see what that is, first of all. And then we'll go back and we'll look at the floor plans and see uh, what we can do about that. All right. All right, I should have looked at the table of contents to see what sheet we should look at first. But anyway, this will work. Just scroll through. It's always a good idea to be familiar with the architectural plans anyway, to go through all of the different sheets. So this doesn't say it. I might be looking at, you know what? I think I'm looking at the wrong. Yeah, I am looking at the wrong, I'm in the right class. I guess we'll just go over to Brightspace and do it that way. So let's see. If I close this down. Let's drag this over.
Building service systems. Building Service systems.
I'm looking here to find, to navigate to Brightspace. I'm doing it on the other screen. Okay, here we go. Quick links, Brightspace. While I'm pulling that up, I'll mention that the next two classes, the next two Fridays are in person, not online. So you'll have me in person for the next two classes. Let's see here now. All right. So I'm in your class and I want to go to content
Oh,
and final project. I think that's it. All right. I hope you can still see my screen. Okay, so I think this is it. All right, so we're looking for wall type C, which is this wall. And change airspace, rigid insulation. Okay, wall type C would be the bond area of the house. And let's see if I can make this just a little bit smaller. The wall type C has brick on the outside. So we can see that it doesn't go all the way around the house. It doesn't go here because there's no brick on this part of the house. So the answer to your question is wall type C, start here and go all the way around, but it would stop here. So for your linear distances, you would measure these distances. One of your classmates just asked you would add these linear distances and then multiply it times the height. So let's go take a look at that wall type C. See, it has brick on it. And if we look at a section, where does that occur? We can see wall type C is right here. You can see that it's 3'6" tall. So that's going to be your height times the perimeter, which will give you the area of wall type C. Does that make sense?
Yes, Professor, I see that you were looking at the first floor. So based on each wall type where it's shown on this plan right here, this dimension slide right here, it determines which floor, I guess, it's on, because it looks like it's just below the first floor. That's why I was looking at the basement dimension plan.
Well, you can see this section cuts through the house at the garage. So you can see that there is no wall type C on this side on the wall that's common with the house and the garage.
Right.
So if we go back to the floor plan.
Me? No, I love your mom. Your mom is.
We can take a look at the floor plan here and we can see.
I just want to keep it documented that nothing is happening and that we both respect each other.
That you can see that that wall that's common between the house and the garage, this is the garage and this is the house, doesn't have wall type C.
Okay.
Everywhere else around there, it does have wall type C.
Got it.
All right. Any other questions about the project before we get started in the content of the course itself? All right. Well, I'll just remind you that this is a very time-consuming project. Therefore, it would be in your best interest to start taking the little baby steps towards finishing. And right now, just calculating the area of the different wall types would help you get started on the project. I have also uploaded to the content area the spreadsheet that you can use in order to answer the very first questions, which are what are the areas of these different wall types? And it's simple math. You take the perimeter and multiply it times the height, and that gives you the area. And you can assume for the calculations right now, we're just trying to find the wall areas, so we can assume that there's no windows or no doors in there, and we will further down in the spreadsheet, we will subtract the windows and door areas from the wall areas that you start originally. So the best way to do it is just to ignore doors and windows and just say this wall type is this height times this length. Put your areas into the spreadsheet, and then later on the spreadsheet will accommodate the fact that there are windows and doors in those wall areas. Okay, any other questions about the project? Okay, so
I have a question.
absolutely, yes.
Are we able to go over the project during your office hours on Mondays?
Absolutely. I'm there. That's exactly what I'm there for, is to help everyone in any way that you need help on this project. And it'd be smart to take advantage of that, definitely.
Okay,
Every Monday,
thank you.
but not just Mondays from 9 to 11. If you're working on it on Wednesday at 3 o'clock in the morning and you aren't sure what's going on, send me a text message. I might
And we
be
can also refer to your YouTube video, right?
You got that right too. There are some YouTube videos there. Maybe we'll make some more specifically for this class to help you through it. But I was just saying, don't hesitate to send a text message at any time of the day. If I'm not available, I won't answer it, but you don't know when I am and when I'm not. So it's okay to send it at any time of the day, any of the 24 hours period. So
Okay, thank you.
good. All right. So attendance will be taken at the end of the class. I still haven't figured out a way to let you self record that you were here in the class, so we just do it right at the end of the class. And I'll just go down through that attendance sheet and we'll mark you here or there. Remember, I don't know if you can access your attendance or not, but I guess I'll put that up on the screen. And if you're here today, then you'll probably get credited for being here today. But if you see any friends who don't have any present marked in the attendance, you might want to tell them because I'm about to submit the records that tell the university whether a student has attended in the first 2 or 3 days of this semester. And if I report that a student hasn't attended, they get thrown out of the class right away, and that's it. You're out. That's the end of the story there. Okay, so we'll do that at the end of the class. So let's see if I can move this out of the way. And we last left off on talking about letting nature deal with things, but not actually following that tested true method of dealing with the cleansing of water, for example. And we've decided that we're going to build, and we have built, huge processing plants like this, which is very expensive, very industrial, or we could let nature do it the way that it has done for billions of years. And somehow we have come along and we've thought, well, we know better. We'll do it. We can do it better. A possible argument, of course, would be that, like in Manhattan, there's no way that we could use the earth to to the area of Manhattan, because it's pretty much covered with buildings and hard surfaces, except for Central Park and some other parks and that, but there's not a lot of area. So the argument could be made that for some places, this is the proper solution, but I think that as you progress out into your profession, that it wouldn't hurt you to ask, as you're trying to solve a problem that you're paid to figure out or participate, contribute to figuring out, that it wouldn't hurt you to stop and say, well, how would nature do this? Could we use nature to do that? And let's see, I have yes, I like to watch a lot of YouTube videos. That's my source of a lot of information. It's also my source of entertainment as well. And as you know, when you're at YouTube, you get all kinds of little videos that pop up, and I often see the videos that pop up that are talking about construction disasters. And I'll show one, and then we'll go to the next one and talk about it. I think if I click on this, there might be a little ad ahead of time because it's YouTube, but we'll get to the disaster in a second.
I live in Michigan. I'm a two-time Trump voter, and I'm not voting for him again this year. Trump is.
Politics has no place in our classroom. That just happened to be an ad that came ahead. But watch this. Watch what happens here with this house. It's a disaster. And I like to watch these kind of things only so that I don't make those same kind of mistakes myself. And I think in that case, when I design my houses, I wrap them entire outside surface in plywood, and you'll see that your class project has plywood wrapped around the whole perimeter, which would stiffen it up. And I think that they failed to do any kind of stiffening of that house, and that's why it failed. But if we take a look at this one, this is also an example on those sites of bad design, when in fact it is environmentally, it's a very appropriate design. And I think that the purpose of this was to demonstrate that this drainage, this inlet for drainage should be lower, not higher than the surrounding area, so that the water can drain into it. But if you take a look at this, this is actually, I'm not saying that it was done intentionally, but this is the environmental way to do it, in that you let the earth percolate, let the water percolate into the earth first, and then when the water level reaches a certain height, then you start to take the water away into our man-made solutions. But I was talking to a gentleman the other day, and he was talking about how, we haven't seen all of these flooding, years and years and years ago, communities didn't flood like they do now. And one of the reasons that they flood now that they didn't flood before is there's a lot of these kind of surfaces, all the hard surfaces. So this is not going to let any water percolate into the ground. This absolutely allows that water to percolate into the ground, which is similar to what that example in Davis, California was. That they implemented things like this, which would allow nature to work properly. But in the event that, it got really, really flooded, then we have this backup system that would take the water and relocate it into another area. So the only reason I'm showing this is I mentioned that I got the master's degree in sustainability, and I didn't tell you why I told you that. And the reason I told you that is that in part of this class, we'll talk about some of the sustainability concepts of that, because that's a very important field. In 2050, 80% of the energy that is consumed by the buildings in Manhattan will have to be supplied, the energy will have to be supplied by renewable resources, which means electricity. And so there's a tremendous opportunity for you in your career to go and try to solve those problems, because that's an almost impossible achievement. If the building owners don't, according to the rules and regulations, if the building owners don't satisfy that requirement, that they will have to start paying substantial fines for not energizing their buildings with renewable resources. So the building owners will be more than happy to hire experts, which may be you, if you follow that path, to show them and tell them and help them achieve that almost impossible goal. So if they have any interest in that kind of focus, I think that could be very profitable for you as a consultant in those fields. Okay, so back to water. So we talked about the water percolating into the ground, and that's where the ground is set up pretty much exactly like I showed you that one example of the plastic bag hanging from the tree, where you put the different filter materials in there to get the clean water. Well, we're replicating what nature does naturally. But inside of the earth is a lot of limestone. There's a tremendous amount of limestone in the ground, which, as the water travels around that limestone, it's absorbing magnesium and calcium from the limestone. And the water is drinkable, but when it becomes saturated with that limestone and magnesium, calcium and magnesium that the water absorbs from the limestone, what happens is that water becomes what we call hard water. And hard water is not a good water for cleaning. In other words, it prevents soap from sudsing. So if we have hard water here at my house, our house, because we have a well, and the water that percolates around the source of water that our well is sucking up, this right here, has a lot of calcium and magnesium in it. So we have to have a filtering system that separates the calcium and magnesium from the water so that we can use it, because if we didn't have that system, then we wouldn't be able to wash dishes, because the soap wouldn't suds and clean and help to clean. Certainly when we took a shower, the water and the shampoos wouldn't suds up. I don't wash my car here, but if I did, that same thing would happen. Laundry, the same situation, there wouldn't be any soap sudsing, which is part of the cleaning process. So that there's a natural result of the water cycle, but it's not a good result for us, so we have to separate that calcium from magnesium. Something else that I wanted to point out that I didn't do before is that as I go through these slides and I see something that seems familiar to me on an exam or a quiz, I often highlight it in red. So when you see something that's in red, there might be a possibility for you to prove back to me later on through an exam or a quiz that you were paying attention when we were talking about that specific topic. So what happens with that hard water is it does retard the foaming or the lathering of the soap and detergents, which is what makes the soap and the detergents work as they're supposed to. And it also can build up in pipes that calcium and magnesium in the water can attach itself to the sides of the pipe that the water is traveling through, and eventually it can clog the pipe completely, or in some cases it builds it up to the point where it actually causes some sort of breakage. It's also damaging to the water tanks. We have Dr. Edwards calls them hot water tanks, and I call them water tanks. And the reason I don't use the word hot water is because well, I guess it could be a hot water tank, water heaters, as opposed to hot water heaters, because you don't have to heat hot water, you have to heat water. If the water's hot, you don't need to heat it. So I call it a water heater, not a hot water heater, although some other people do call it that. It's a little pet peeve of mine. When we talk about water heaters, they're not hot water heaters, they're water heaters. But we won't be quizzed on anything like that. So, okay. So let's talk about the system that we have here at our house, and it's very simple, very typical in the methodology of separating the magnesium and the calcium from the water. And one of the methods is called zeolite, or the ion exchange process. So we soften that by extracting the chemicals from the water in order to be left with simply the water that is not containing calcium and magnesium, which means that it's no longer hard water. So what happens is we have to put some sort of a solution into a big tank at here, or in any water softening. You in Brooklyn and Manhattan, up in Harlem, you don't have those issues because that water is not drawn out of the ground. It's coming from the reservoirs up. But if that water were hard, the municipality would extract the calcium and the magnesium prior to delivering it through pipes into your own residence. But here in a residential setting, a suburban residential setting, where we had to put a well down a couple 100 feet in order to get to that water source, that water that has percolated through there does have that, and it has to be separated. So we put a chemical in, we put a product into the water that absorbs the magnesium and the calcium out of the water. And so then when it has absorbed that magnesium and calcium, we throw that portion of the water, we throw that away. We put that into the sewage system. But the water that doesn't have those chemicals in it any longer is what we use for drinking and bathing and washing. So the ion exchange process, or the zeolite, is a chemical process that absorbs the bad stuff out of the water, and we discard that portion of the water away while we keep the good stuff, the good portion of the water. And it's like if you had metal in your water and you put a magnet in the water, the magnet would grab all of the metal, and then the water that remained would be free of magnets or metal. We're just trying to extract the bad stuff out of that water so that we can use the good stuff. So also remember that in that water cycle, that circle that I showed and shared and explained with you, that one of the designs of this system, this natural system, is when the rain comes down through the sky, it's designed to grab the impurities, the imperfections, and the pollutants out of the air and drop it back into the ground so that the ground can filter that out. But now we are burning fossil fuels and we're also throwing carbon up into the atmosphere. Much of it's wrapping around this planet, not escaping out into the universe. But some of it doesn't even get to that point when the rain hits it and pulls it back down to the earth. So then it becomes, we're adding pollutants into the air. The rain is trying to still clean that out, but it's taking more than it originally had to, because before we started burning fossil fuels, we didn't have all that carbon in the air. But that is also acidic. It's bringing acidic water back down. Now, on a scale, we measure how much acidity is in the water. And when we have a high level of acidity, it can be very corrosive and damaging. It can also, when that water hits your car, the paint on your car, it also deteriorates that in a small amount. But if you left your car out for 10 or 15 years, you can see what happens to the paint jobs on the older cars. You know, and some of that is because of the acidic water coming down, the rainwater coming down onto those surfaces, like the surface of the exterior of a car. So we have a way to measure that, and it seems contrary to what I would assign as a value system. But if it's neutral, it is around 7 on the pH scale. If it's highly acidic, the number actually goes down closer to the 0. And if it's basic or not having a lot of acidity to it, that's a high number. So if I said I was I put a couple, I'll put a old coffee can outside, and the rain went into it, and I collected the rain in there, and I measured it, and I called you up and I said, well, I measured the acidity of it, and it's coming out at 7. You would say, well, that's neutral. If I called you up and asked you how is that bad or good, you'd say, oh no, it's neutral. And if I said, well, I measured on a pH scale and it's 14, you would say, no, that's all right. That's basic. If I told you I got a nice low number of 0 and I was all excited about it, you'd say, well, no, that's not good. I remember from Professor Bryce's class, that's very highly acidic water. You got some bad stuff coming in through the atmosphere. What's next here? Okay, yeah. So now we start to apply the movement of water into our daily lives. You know, when we walk into our building on campus, what do we think? Do we say, oh boy, I hope the toilet's flush, I hope there's running water on the 4th floor before I get into class today? No, because we expect that it will be there. But if you think about it, generally the water is coming in from below the ground. If you look out the windows in our building, or basically if you look out the windows of any building, you're not going to see pipes of water suspended in the air anywhere. And one of the reasons we don't do it that way is because water freezes, and we know that in New York it gets very cold, and sometimes it gets below the freezing level of water. And we also know what happens when water freezes is that it expands. So it's very likely that, or probable, that all the water that's supplied to the buildings in Manhattan and Brooklyn come from below the ground. And once you get below 3.5 feet, unless it's an extremely severe cold winter, the ground never freezes below 36 inches or 42 inches below the grade. So it's very likely that that water main that's coming into your building is at or below what we call the frost line, which is, regardless of how cold it is outside, even for a long period of time, the earth is not going to get cold enough to freeze those pipes, and that's why the pipes are laid underground inside of the earth to take advantage of the insulating value of the earth. But once that water gets to it, it comes into the cellar. Well, somehow we have to get that water up to all of the different floors, including, of course, the 4th floor that our classes are on. And it's there when you walk into the bathroom, when you try to take a drink of water out of the water fountains. The toilets flush, there's water to flush the toilets, the sinks operate to wash our hands. But how does that water get up there? Well, it gets up to those levels by being pumped. There's a pressure level of water is pressurized to come to our meter. Once it gets to the building, there is a meter there that measures how much water this particular facility, our facility, would use. And whoever is delivering, whatever utility company or municipality is delivering that water to our facility, wants to be paid for the amount of water that we use, and that's why the water runs through a meter. Now, as that water runs through the meter, there's a device in there that measures how much water is being used, and at the end of the billing cycle, whatever that is, weekly, monthly, quarterly, annually, or whatever, there's a bill that arrives based upon the amount of water that went through that meter, and the user, the operator, if it's your house or your apartment, you may have to pay for that, or maybe it's included in the rent. If you own a home, that's going to cost. You're going to have to pay for that. It's for the municipality delivering it. In my house, we don't have any municipal water. We have a well, as I said, so we don't have to pay for the water because it's nature gives it. Nature doesn't have a meter on its water supply. But anyway, we have to get that water up. Somehow we have to get it up. Now, other ways to do it is we might take the water and pump it up to the roof. And then gravity will pull it back down. So if our water lines were up in the sky somewhere, we could use gravity to bring that water back down to our facility. But somehow we'd have to pump that water up to those to begin with, to get those way up high in the sky. But then we could use some sort of a collecting device on the roof, make sure it's insulated so that it doesn't freeze, the water doesn't freeze, because everybody knows from putting water or soda or some sort of liquid in the freezer to make it get cold quicker, and then we forgot about it, the ice expands. The water, when it freezes, it expands, and it can damage, destroy your container, whatever it is. And if it's glass, then it's a big mess. If it's plastic, it's still a mess, but it's not as big of a mess. But we would insulate this to allow that water not to freeze, and then gravity will bring it down for us. Okay. The same thing here. In this case, what Dr. Edwards is identifying is that the pressure from the municipal supply is enough to push the water all the way up. But in this case, the pressure from the municipal supply is not enough, so that somehow it needs to be pushed up into the different floors. And that would be a tank system. This would be a non-tank system without a pump, or with a pump, but without a tank. So this would store water from here and pump it up. This would just simply pump it up as it's required to happen. Now, we're building up to a use, we've laid a little bit of a concept about what we need to do. And now we need to do a little bit different mathematic formulas here, which you don't need to be able to duplicate this or replicate it. But what Dr. Edwards has proven here in his logic is that what he's trying to prove is that the size of the pipe has nothing to do with the amount of pressure needed to push that water up in the facility. And he's saying that if you double the diameter of the pipe with the height that you're trying to push that water up, that if P1 equals force times area, so the area of this times the force will give us our P1, which is our pressure. Dr. Edwards is saying that P2 is going to equal 2 times the force divided by 2 times the area, which equals P1. Now, this is not a math class. You don't have to understand anything more than the fact that Dr. Edwards says the size of the pipe doesn't matter in terms of how much pressure you need to get the water from one elevation to another elevation, to a higher elevation. And so if you're thinking, well, I guess maybe Professor Bryce is going to have one of the questions about how much pressure it takes to get water from one point to another, you'd be correct. But if you saw that on a quiz or an exam, that question, and I didn't tell you what the pipe size was, what is the diameter of the pipe, your answer that not enough information because there's no pipe size would not be a valid answer. That doesn't matter. And that's the point that Dr. Edwards is trying to make here, is that regardless of the size of the pipe, big or small, the same amount of pressure needs to be applied in order to get that water from one elevation up to another elevation. We're talking about the force or the pressure it takes to get that water up to the 4th floor where we need to use it. How do we get it up there? Well, it's going to take some pressure. How much pressure is there going to take? And yes, there is a formula for that. And Dr. Edwards has provided that for us. And really what it is here is that for every 12 inches of water, now we're talking about H now, how high do you want to push that water? Well, if I wanted to push that water up 12 inches or 1 foot, I need to apply 0.433 pounds per square inch of pressure, irrespective of pipe size. So Dr. Edwards has provided a proof that the pipe size doesn't matter. So it doesn't matter how big or how small that pipe is. For every foot that you want to raise water, you have to apply 0.433 pounds per square inch of pressure. And we do that with a water pump that provides the pressure necessary to get the height, to get the water from one elevation to another. So if we take a look at this formula, we say, well, we're just not going to ever want to raise it up 12 inches. We want to raise it up from floor to floor. So in the event that the floor to floor dimension was 10 feet, then we would say, well, how much pressure do we need to get the water from the 1st floor to the 2nd floor? We know the height of that floor to floor dimension is 10 feet. Then we would multiply 0.433 times the vertical distance, 10 feet, okay? 1 foot needs 0.433 PSI. 10 feet are going to need 0.433 times 10 PSI. So we need to figure out, well, how much water pressure do we need to get the water from one floor to the next, or from the incoming location all the way up to the top floor? How much pressure do we need? So let's see what he has here. Okay, So now let's analyze what's going on with this, because you will definitely see a story problem, which I'll give you some information in a paragraph, which will have useful information inside of that paragraph, and it might have some information that's not useful, but it's just filler for the paragraph. And I'll expect you to extract the important information from that word problem or story problem and apply the information that you've extracted to the proper formula to answer the question about, well, how much pressure do we need to provide to get the water from one spot to a different elevation in the building. And so remember, we talked about the water meter. We said that that water meter is measuring how much water passes from the supply side, which is coming from the utility company, to the usage side, which is the side of the building that's actually going to consume that, the consumption. And there's a meter in between. And that meter is going to eat or consume between 5 and 10 pounds per square inch of pressure. So right off the bat, what Dr. Edwards is saying is that when that water comes into the building and passes over that meter, which is measuring how much consumption of water there is, we're going to lose 5 to 10 pounds per square inch of pressure from whatever the municipality was providing that water to the meter to get the water to the meter. Because remember, the utility company's got to push that water through the pipes to get it to our facility. And so therefore it comes pressurized already. But once that pressurized water passes across that meter, it's going to cost us 5 or 10 PSI just to get the water through the meter, because there's resistance on the whatever device is measuring the flow of water from one side to the other through the meter. And Dr. Edwards will say, we're always going to figure that we're going to lose 5 to 10 PSI. So if the pressure on the utility side was 100 PSI, and we measured the pressure on the other side of the meter, it would be 100 minus 5 to minus 10 PSI. So that's minus 5 PSI or minus 10 PSI. So if I said to you, the water pressure at the meter coming into the meter is 100 PSI, what's the water pressure on the other side? And you said, well, Professor Bryce, it's between 5 and 10 PSI loss at the meter. You're telling me we started out with 100 PSI, therefore it's going to be 95 to 90 PSI on the other side of the meter. Now, think of that meter as being the turnstile at the subway, and assume that the subway, the cost to make that turnstile operate to let you through was $5 to $10. And you started out on the outside of that turnstile with $100 in your pocket, and you had to pay to get through the turnstile of either $5 or $10, then on the other side of that turnstile, you would have $95 or $90 remaining. So if you started with $50 on the one side and it took 5 to 10, then you would have 45 to 40. So it depends on what the pressure is on the one side, but we can use a constant of 5 to 10 PSI loss just right there going across the meter. Now, also, we're trying to calculate how much water pressure we need to provide. Well, the water pressure along the lengths of the pipe due to internal friction is going to be a number as well, which we can calculate from a chart. And it's taking into consideration the material of the pipe, the internal pipe diameter, and the water flow rate. So you can look at a chart and say, well, the pipe material is A, the internal pipe diameter is B, and the water flow rate is C. And where you find an intersection of those three pieces of information would tell you how much pressure is lost across that amount of pipe. But we don't do it that way. That's too complicated. This is not a course that dives deep into any of these systems to the point where you would be an expert at it. It's a course that just gives the broad stroke concept. And then if something that you learn in this class or another class is really, really interesting and fascinating and you enjoy doing it, well, then that might be something that you would do in your career and pursue that academically in another method. And the same thing here. We're not going to get into that reading that chart to figure out how much pressure is lost. It's going to tell you, okay? I'm going to tell you how much pressure is lost. So that's always going to be part of the story problem or word problem. I was going to say, well, we're going to lose this much water pressure along the lengths of the pipe. Now we're talking horizontal lengths. We haven't talked about vertical yet. That's something, the vertical water pressure loss is something that I will ask you to calculate. The horizontal water pressure loss through the pipes is something that I will tell you, okay? So that you don't have to go to the chart and look at all of the different variables, the material of the pipe, the diameter of pipe, the water flow rate, because if you think about it, on the inside of a pipe, if it's really, really smooth, there'll be less resistance to push that water through the pipe. Therefore, it will require less pressure, okay? And we might be saying, well, wait a second, Professor Bryce, you just told us, or Dr. Edwards just told us in a previous slide, that the size of the pipe doesn't matter, and that's true for the vertical pressure calculation, but it is not true for the horizontal pressure calculation. So I'll just give you that information. I'll tell you that the pressure drop due to horizontal pipe is X PSI. I'll just give you that. I'll just say that. You don't have to calculate it, do all the math and do the calculations. But what I may or may not tell you is how much pressure is lost as the pipes bend and curve and dip, and well, not dip, because that would be a change in pressure due to gravity or pressure to push it up higher. But the pipes that come into the building don't go directly to the place where we want the water to come out. It has to snake through walls and different partitions and floors and everything to get through to the place where we want it to be. And it's not a straight line. So we're going to lose pressure again. We're trying to figure out, well, where are we losing pressure and what is that pressure going to be? And for the bends in the pipe, we're going to say, for purposes of this class, that it is equal to the pressure along the horizontal pipes, which I've already given you, okay? So if I were to tell you that you've got through the turnstile at the subway and it cost you $5 to $10, but now just to walk from the inside of the turnstile to the subway is going to cost you another X number of dollars, then you have to subtract that from the amount of pressure or dollars that you started out with. But not only am I telling you that it's going to cost to walk from the turnstile to the subway in dollars, but it's also going to cost every time you turn, it's going to cost some money as well. As your path turns left or right, you're going to have to pay some more money. And how much money do you have to pay? Whatever it costs to walk the straight line. So if I tell you to go from the inside of the turnstile to the subway is $10, then it's also going to cost you $10 because it's not a straight line. Because you're going to turn left, you're going to turn right. You're going to turn left, you're going to turn right. To get to there, there's a person standing there. Every single time you make a turn, you have to give them some more money. And the amount of money you have to give those people because of the turns that you're making is equivalent to the amount of money that you have to pay to walk the straight line. And how much money is that you have to walk the straight line? I'll tell you. I'm not going to ask you to figure it out. I'll tell you. So I'm going to say to walk the straight line or for the water to go through the pipes in a horizontal distance is going to be X PSI. You need to remember to add what we call the equivalent length, the EL, which is equal to the amount of pressure lost in just going in a straight line. So if I say you lose 100 PSI on your horizontal run of the pipe, I won't tell you that you're going to lose for the equivalent length, probably. And if I don't, do not forget to add the equivalent length pressure drop for the water as it negotiates the bends and turns in the pipes and the fittings and the elbows and the T's and the valves. We call that the equivalent length. So I'll give you the horizontal pressure loss, double it to come up with the horizontal pressure loss and the equivalent length pressure loss. Okay, now we've got that water. It started at the building edge. We have a meter. It went through the meter. Then it went a long, long straight line. And then it does all of these curves and turns and everything. And now we want to get it to go up. We want that water to go up to another level. Well, we already know this is important, certainly important because it's in red, but we know that to get it up, we want it to be 0.433 PSI per foot of vertical distance now. And that's something that I'm not going to do the math for you, but I'll very likely just say, well, it's the 100 feet. And if I said, what's the pressure needed to push the water up 100 feet? You'd say, well, that's an easy one. Thank you for an easy question on an exam or a quiz. And that would be 100 times 0.433. And that will tell you what the pressure is to make that water go up to the top. Now, as a safety factor, just like as you're navigating through the subway, you don't want to come out the subway at the other end without any money left over. We want a safety factor when we get to the last height fixture on that building, and that's 25. So you got $25 folded up, stuck in your wallet. You always want to have that extra $25. You also always want to have that extra pressure at the end. So it may be a little bit confusing right now, and it may not be a little bit confusing where you're going with this, Professor Bryce. Well, here's where I'm going with it. We're actually going to have an example here. If I said in a story problem, I told you all of this information, and you harvested that information out there, and I said the water pressure loss across the meter. Now we got the utility companies bringing water to the meter, and it's at a certain pressure, but we don't know what it is yet. And I say, well, we go across the meter, we're going to lose 5 PSI. I'll tell you the water pressure through the lengths of pipe are going to be 10 PSI. And you're going to say, well, okay, if it's 10 PSI for the horizontal lengths of pipe, I've got to double that. I've got to add that same amount, the equivalent length for all the bends and turns that it's going to take. And now the height of the fixture above the main is 100 feet. Well, everything else is in PSI, and all of a sudden I've given you a distance. Well, what that distance is 100 feet. Well, okay, we're going up vertically 100 feet. Well, how do I convert that into PSI? You multiply 0.433 times 100, and that's 43.3. You can see that that's how we got that 43.3 PSI. So what's the question here? What is the minimum water pressure required at the water main? So if these were all dollars, how much water would you have, how many dollars would you have to get into the building and reach your destination? And the answer is, well, let's do some math here, okay? Number one, 100 feet. So we know that this is going to change to 43.3 PSI. We add everything else together, 5 plus 10 plus 10 plus 43.3 plus we want that extra cushion at the end, an extra surplus of 25 PSI. we add that all together, and the minimum water pressure at the main in order to satisfy all of this, meaning that the minimum water pressure that the utility company must provide to us is 93.3 PSI. If we want that water pressure to push the water all the way up that 100 feet in our building. In the event that the water pressure from the utility company isn't 93.3 PSI or greater, then we have to provide that water pressure on the other side of the meter with a water pump. So let's do another. Let's take the same situation. The water pressure across the meter is 5 PSI. In this example, the water pressure lost through the lengths of pipe is 15. You have to remember to add the equivalent length, which equals the water pressure lost through the pipe lengths. So that's 15. And now, Dr. Edwards has told us what the water pressure is at the water main. This is how much pressure is coming in from the utility company. And he's saying that we still need that surplus of 25 PSI. Different question this time. What's the maximum height that we can push that water up? Now we know how much, we know all of this information, but we don't know what the vertical distance is, but we can figure it out. So the water pressure left to support the lift of water at the highest fixture would be the water supply pressure. That's what came into the building, minus all of the losses of water pressure through the horizontal pipes and the bends and turns. And that surplus, we want that extra 25 PSI, the last fixture water pressure. So do we have that information? 92.5 is the water supply. And what did we lose? We said we lost 5 plus 15 plus 15 plus 25. So we add all of those together and subtract that from what we started out with. And that means that we have 32.5 PSI remaining. In other words, we came in with $92.50, crossed the meter, cost us $5, walked a straight line, cost us $15, turned some corners. Every time we turned a corner, our total loss there was $15. And we wanted 25 bucks left in our pocket when we got to the subway. Well, that's 32.5 PSI that we have left, okay? So we need to get that 32.5 PSI. How high can we go? Well, we know that we have 0.433 PSI per foot. And if we have that 32.5 PSI, that's a surplus. That's the pressure that we have left in our facility. We want to push it up. How high can we push it up? Divided by that 0.433, and it comes out to 75 feet. Now we know we can put that water up 75 feet into the air with the surplus of pressure that we had extra from the utility company. So we'll do one more. And then we'll pause, see if anybody has any questions. But number 3 is now we know the water pressure across the meter, how much we're losing as we cross through that turnstile, how much we lose through the pipe lengths. Okay, remember, we have to double that because we have to add the equivalent length. So we're going to do that again. The water pressure at the main, boom. The water pressure that we need as a surplus, 25. And the height of the highest fixture above the main is 300 feet. So now the question is, what is the minimum pressure boost required of a pump? Well, what Dr. Edwards is suggesting here is that we have a certain amount of pressure coming in, you have a certain amount of money in your wallet. When you get to that turnstile, you gotta pay the 5 PSI. When you go through the pipe, when you walk horizontally, you gotta pay 15. Every time you turn a corner, you gotta pay 15. Water pressure at the main, that's how much money you have in your wallet, all right? That's extra 25 surplus. And we know we gotta go up 300 feet, so we can calculate all of the money that you need to spend. But what Dr. Edwards is suggesting is at some point along that line, you're gonna have to borrow some money to get to the subway because you don't have enough. You're gonna need to borrow, and he's asking, well, how much are you gonna need to borrow? And so here's the answer, okay? 5 PSI to go through the water main, this 15 for the friction, 15 for the fittings, 25 for the last fixture. Remember, we want that surplus. And then we said we're going up 300 feet, so we multiply 300 times 0.433, and that gives us 129.9. So we have a total of 189.9 PSI that it needs for us to satisfy the pressure requirements in the facility, or you have $189.9 it's going to cost you to get from the outside of the turnstile to the subway car, all right? But you only have $53.9 in your pocket, or the pressure that came from the utility company was 53.9 PSI. We need 189. We calculated we need 189 altogether, and the water pressure at the main is 53.9. So what's the difference? Well, we need, subtracting those two, we need to provide additional pressure to that water through the use of a pump of 136 PSI. So if you're in the facility, we're working on something, and I tell you, go down to Home Depot and buy a pump to pump that water up. You would look for a pump at Home Depot that would provide at least 136 PSI. But if we're just standing there in the facility, we would want to figure out, well, how much PSI do we need to provide to that water? And we would do it simply by this. Well, what's the pressure at the outside of the building? In this case, it is 53.9 PSI. And then we can add all of these together and find out that we have a surplus of 53.9 and a deficit of 189.9. So how much does our pump need to provide? 136 PSI. So I'll pause here and ask if anybody has any questions about anything or any comments or anything like that about the topics that we discussed or anything else today.
No, I think you explained it pretty well. But even if I do have questions, I'll probably just go back to the recording. But thank you.
Okay. Well, that's good because it will definitely, there will be some questions like this on the midterm and on the first quiz as well. Which is just, it's maybe a little fuzzy first time around because maybe you've never thought about this before. How does the water get up there? Well, we push it up there. And how do we push it up? What units of measurement do we use to push that water up? Pounds per square inch. Okay, so now we know how we do that. Now you know how to calculate it.
Professor,
Yes.
you mentioned that you don't personally pay for the municipality, but would you have to pay like a water pump company to pump the water up from the wall?
No.
Oh.
If you're talking about our house, yes, we bought the pump, okay?
Okay.
What we do have to pay for, though, is because we are connected to the municipal sewers, that normally the sewer company, the municipality for the sewers calculates how much water you use, and that's how much you have to pay in sewer fees. But since they don't have a meter on our water, because we pump it out of the earth for free, and we don't
Yeah.
have, we have to buy the pump to pump that water up, but we still have to pay the sewage rate, so the sewage utility company, which is governmental, just counts how many toilets we have in our house, and then that's how they calculate how much sewage we put into the sewage system every month. But if we had a septic field, and that's something that we'll talk about as well, if we let nature do that, handle the sewage, then we wouldn't have to pay for water and we wouldn't have to pay for sewage either. But because I live on a lake, the municipalities don't allow us to put in septic fields, and we'll talk about septic fields a little bit later. But that's the natural way that the earth processes the sewage from a facility. But we're not allowed to do that here because some of that contamination some of that water, the earth wouldn't clean all of that sewage, and some of it would percolate into the lake, and that would be a bad thing. So, this is a good point to tell you a little bit of story, but when 35, 40 years ago, when I was looking for a piece of property to build on, I was driving around the various suburban cities in the metropolitan Detroit area, and I found the lot that I ended up purchasing, and it was a very desirable piece of property because it had a southern exposure, meaning that the property sloped from the street to the lake with a southern exposure, which meant that I could build a solar house. And it was on a lake, and it was in a very affluent city where the professional athletes mostly purchase their houses or build their houses, and the very successful doctors and attorneys or other businessmen have chosen to live in this city. So it's a very desirable city. And I found this piece of property that was really, really underpriced, substantially underpriced by in my opinion, hundreds of thousands of dollars cheaper than it should have been. But I'm not one to quibble with someone who wants to sell a piece of property of this kind for substantially less than it's worth. So as soon as I saw it, I bought it. I said, okay, fine, I'll take it. Didn't do any research or anything like that. And, closed right away, no questions asked, because it was too good to be true. And then I drew my house plans and went to the city to get a permit to build this house. And they said, you don't have sewers in that neighborhood, and you're not allowed to build a house without sewers. And I said, well, I'll just put a septic field in. And that's when they told me that, you're on a lake. We don't allow septic field. We don't allow nature to do that because it doesn't cleanse the water 100% before some of that water would get to the lake. And we don't want raw sewage in our lake. So I purchased a very beautiful piece of property, which all I could do is bring a picnic table and a picnic and come out on the weekends. So it always pays to do your research, but in the end, the solution for me for that was to convince my neighbors to pay to put in a municipal sewer system, which I successfully did. And so we put in a municipal sewage system, connected it to the municipal sewer, and then I was able to build a house. So we'll talk about septic fields a little bit later, but there was a reason why the property was so inexpensive, and it was because it was not buildable. You couldn't build a house on it. That was my mistake, but I worked around. Fortunately, I was able to actually work around that. So yes, long answer to a short question. Don't have to pay a pumping company to pump it because I just You know, you can buy pumps that will pump the water, which we did. Pumps it into the house, we get the pressure. And that's how it works. Nature provides the water, but nature does not distill the sewage. So I think we're pretty close to time to take any other questions that anybody would have, or we'll just go right in, and then we'll go right into attendance. Any other thoughts, comments, anything like that?
How do you know when to multiply or divide the 0.433?
Well, you would always multiply times 0.433 because you would be going in a vertical direction. You're going up. So you always multiply. The only time you would divide by 0.433 is if you're trying to calculate how much how high you can do it. So if you know how high you can push that water up with the pressure that you have. So if you had, for example, in this case, we had 129.9 PSI left over before we went vertical, the question would be, well, how high can you go with 129.9 PSI? And in that case, you would divide by 0.433, and the answer would be 300. So that was I think that was the second question, second example, where the question was, well, how high can it go? Well, you take your surplus of pressure and divide it by the 0.433 if you're trying to determine how much height you can push that water up. If you know how high you need to push the water up, then you multiply that distance by 0.433. But if you're trying to find out how high you can push that water up with the amount of pressure that you have, then you would divide. Does that make sense?
Yeah. Okay, that clarifies it.
Yeah, so let's say that your car gets 32.5. Your car has 32.5 gallons of gas in the tank, and you get 0.433 miles to the gallon. Then to find out how many miles you could go, you would divide the miles per gallon time by the amount of fuel in the tank. So this is how much fuel we have in the tank. This is how far you can go per mile with that fuel, per gallon rather, and that would tell you the distance you could go. This is how much pressure we have in the tank. This is how much pressure it takes per foot to go vertical. And that would tell you then how much vertical distance you can go with this amount of pressure. So if you think about that, if you're trying to solve for vertical, then you're going to divide. If you're trying to find out how much it takes with a known vertical distance, then you would multiply.
All right, thank you.
Anybody else? Any other questions? All right, so I'm going to go to attendance, and I'll bring that over on the screen, and we'll go through that. And we'll be marking, I hope you can see this, and I'm going to edit that, and I'll just call off your name. And if this is for today, which is the 13th. So Bobby, I saw you come in. Are you still here?
Yes, I'm here.
All right, present. Damien?
I'm here.
All right. Samuel?
Here.
Mitch?
I'm here.
All right. Usami?
Yeah, I'm here.
I know I butchered your name. I'm sorry.
Nice.
Ryan?
Nice.
Yes, I'm here, Professor.
All right. Christian?
Here.
Brandon?
Here.
Ishmael,
Here.
Justin,
Here.
Ramey. Ramey, are you here? David? David, are you
Hello, I'm
here?
here. Sorry, my mute button messed up.
You David or Ramey?
David, I'm David.
Okay, great. Naramfar?
Here, Professor.
All right, I know I butchered your name too. Nicholas?
Yeah.
Abdul?
I'm here.
Chris?
Right here.
Thank you. Bernadette?
Here.
Thomas? Tomas?
I'm here, Professor.
Edwin?
Here.
Karen Deep?
Here.
Brian?
I'm here, Professor.
Dion?
Here.
All right, one to go. Amir? Amir, are you here? All right. If we don't have any other questions,
Professor.
say it again. Somebody say something?
Yeah, Professor, I mailed you about the first day class attendance. I put the wrong date. So did you took my attendance or not?
Yeah, I think I responded to you and told you that there was no class that day, like.
Yeah, I put the wrong date for that.
Yeah, I gotcha.
Okay, thank you, Professor.
All right, so any other questions? All right, then close enough.
My apologies. I just wanted to ask you, what happened with the slides? We won't be able to get them, or
You can watch the videos that will have the slides in them, but Dr. Edwards has asked me not to provide the slides for you.
all right, okay, not a problem. Thank you.
I can't. Well, it is a problem because it'd be a lot easier if I could share those slides with you, but I can't. So that was your answer to your question. All right, so I guess next Friday we have a class and I will see you in person, and then the following Friday after that we have a class and I will see you in person then too. And Monday 9 to 11 we'll have our office hours. So if there aren't any other questions, I'll see everybody next week.
Have a good day, Professor.
All right, Professor, take care.
All right, take care, Professor. Take care, Professor.
Good day, everybody.
Take care.